Okay. One thing about graphs, if you have to, calibrate the axes so that, you're going by 2s or by 4s, make sure that you're consistent. So what I mean by that is, so if you're going by 2s on the x-axis, first of all, you don't have to do the same on the y-axis. You could still go up by 1s on the y-axis, okay? They are independent of one another, right? One thing to watch out for, however, is to make them uniform. So if, this is 2, 4, you can't make the other one like 7, to suit your needs. You know what I mean? Like if you have, let's say, data points that you're plotting, you can't make that like that to suit your needs. You still have to go 2, 4, 6, and then if 7 happens to be in the middle of 2 corners, then fine. Am I getting my point across? Yeah.
I saw in the book, they went 2, 4, and then he did like a broken line over.
Okay, so that's another thing. If your numbers are, let's say, in the, like it starts from 20 and it goes to, 50, and there is nothing from 0 to 20, you can break it up. So you can like literally cut that part of the graph off, but you have to show it. And the way you show it is, so let's say, you go 1 and then 2, and then there is nothing else, until let's say 35. You can make a little squiggly, and then you can do that. This is, however, if you like the squiggly over there is kind of uncommon. The more conventional way to do it is you start off with that squiggly line, and then you continue, and this you can make like 25 or 2,500 or whatever.
Or what if you go 1, 2, and 4?
Huh?
What if you want to use
like you have a 1 and then you have a 25?
Yeah.
Then you just have to put the whole thing. Yeah. Okay, so let's go to 2.2 and talk about polynomial functions. We always, we come across this once in Algebra 2, and then we've mentioned this term before, polynomial functions. So polynomial functions are this. They have variables raised to exponents where the exponents are whole numbers. So what are the whole numbers? Where do they start? Is -3 a whole number? It's an integer. Is 0 a whole number? 0 is a whole number. Is 1 a whole number? Yeah. Natural numbers start at 1. Whole numbers is 0, 1, 2, 3, 4. So polynomial functions are such that exponents are whole numbers. So that's 0, 1, 2, and so on, okay? And so you can have, x to the n is a whole number, and then each of the terms have a coefficient, right? And that's any real number. It could be 1, -5, 2/3, √7, whatever, any real number. There is no restriction or no requirement that it has to be rational or integer or whatever, okay? The above function is a polynomial function of degree n, right? And you remember degree is the what? It's the highest exponent in the polynomial function. And then the coefficients, right? If this is the exponent n, the coefficient that belongs to that term is an, right? And so how do we usually write polynomial functions? It'll be like something to the 4th, then 3rd, then 2, then 1. They go down by 1s, right? So if I start with the highest exponent, 4, then it's -1, -2, -3. So it's n, n-1, n-2, and then all the way down to 2, 1, and so on. Okay. So the leading coefficient is the coefficient of the variable with the greatest exponent. not necessarily the first one, because they could be written in mixed order. Okay, so we look, these are some of the very basic polynomial functions. A constant function, right? Does that follow the pattern? You know, an example is f of x is equal to 3. Where's the variable? It's really x to the power of 0. So there is a variable, there is an exponent, but the exponent is 0. Okay? A linear function where you have y equals x to the 1 plus 3, right? So what's the degree of that one? 1. And then the next one, what's the degree there? 2. All right. So, okay, when we graph a polynomial function, last chapter we learned that the domain for all polynomial functions was what? All real numbers. So that's one thing that we have to remember about polynomial functions is polynomial functions are defined and continuous for all real numbers. You can draw a polynomial function without taking your pencil off of the paper at all. Okay? Here are some examples that are not polynomial functions. This one is not a polynomial function because of the discontinuity. And this one, we will talk more, you will learn more about it in calculus. Basically, because it has a sharp corner, it's not a polynomial function, right? So that sharp corner makes it not a polynomial function. That's an absolute value, right? Which doesn't fit the pattern of this. Okay? It has to do with the slope, but not that it's linear, because the slope of this polynomial function is also linear. Okay. All right, so remember what we talked about. If you have an even degree polynomial, the graph looks like x squared, right? Like if you have x to the 4, x to the 6, and so on. This is from last night's homework. An odd degree polynomial resembles the graph of x cubed. So if we were to graph one of these, right, this is definitely a polynomial. So again, here we have 4x to the 6, exactly like what we did yesterday. The vertex, this is going to look like a parabola, like an x squared. So the vertex is at 0, 0. Okay. The 4 is a vertical dilation. So basically, when x is 1, how much is y? 4. Okay. And then when x is 2, it's going to be way bigger. All right? Okay, in here, this is a cubic function, but it's moved to the right 4 and up 1 unit. So right 4 and up 1 unit. That's the center. And now, just like a cubic function, if I go from the center over 1 unit, I go up 1 cubed. Over to the left 1 unit, I go down 1 cubed. And then if I go, let's say 2 units, right, I'm going to go up 8. No, it's fine. 8 and then down 8, okay? So if I go to the left 2 units, I go down 8 to negative 9, let's say, right? And so similarly, it'll go that high up. Okay? All right. So let's talk about the leading term test. Okay. We can take the leading term of any polynomial function and from that figure out the end behavior. I kind of got you in, I introduced it to you in the last chapter, but we're going to do it for real now. So, take a look at this one. This is a function. Okay, first of all, so is the exponent here odd or even for this one? Odd, right? And it says so here. The exponent is odd. And we know that an, the leading term, is positive. So for example, this would be, y equals 3x to the 5, minus 2x, blah, blah, blah. Like, I don't care about that. All I care is that leading term has an odd exponent with a positive coefficient. Okay, so that's what we have to look at. What about this one? If one goes up, one goes down, again, it's an odd, but because it's going down on the right, there is a negative coefficient, right? So this would be like, negative 3x to the 5th. And then, it would continue with some other polynomial function stuff, which I don't care about. So what I'm trying to say is it's that leading term. It's the term with the highest exponent that will determine the end behavior. That, one end will go up, one end will go down. Okay? Here, this could be a long polynomial on the bottom with like 8 terms. What determines the end behavior? That both sides go up. That's the leading term. And this, what would given a graph like this? It's a function where the leading term will have a positive, an even exponent and a positive coefficient. And then, this polynomial could continue all the way down to a constant. I don't care about that. That doesn't have anything to do with the end behavior. Here, similarly, it could look like, y equals negative 2x to the 6th, and then continue with other terms. What do I mean by continue by other terms? This is what I mean. You could have a polynomial like this. This has 1, 2, 3, 4, 5 terms. Okay? What determines the end behavior, right? So I need to describe the end behavior of this. What determines the end behavior is only the first, not the first term, the term with the leading coefficient. Okay? The leading term, sorry. Okay, this is called the leading term test. Leading term test. Okay, how do I figure out the leading term? It's the one with the highest degree. So between these, it's the first one. You have to be careful to take the plus or minus with it. Okay, now, when it says describe the end behavior, I want the limits as x approaches positive and negative infinity. All right? So, here is what you're going to do. The answer that you're going to give me is the limit of f of x as x approaches negative infinity and as x approaches positive infinity. Those are the answers that you're going to give me in that notation. Now, let's think about why the leading term is the only one that matters. Usually, when we graph a function, we're at the origin, right? X equals 1, 2, 3, negative 1, 2, 3. The most is like x equals 10, okay? End behavior is when x approaches infinity. Like when x is 1,000,000, okay? So, let's suppose x is 1,000,000. Now we come here, and I have 1,000,000 to the power of 4. How many zeros is in 1,000,000? Okay. To the power of 4? 24 zeros. 24 zeros. Think about how big a number that is. And that's not even close to infinity, by the way. That's like very near. Okay? So now we have something with 24 zeros. Versus the next one, if it's 1,000,000 cubed, how many zeros does that have? Only 18 zeros versus 24 zeros. How many times bigger? That's 6 more zeros. That's 1,000,000 times bigger, right? So as the numbers get closer and closer to infinity, okay, 24 zeros is huge compared to a mere 18 zeros. So more and more, that leading term will have a greater and greater effect, and everything else will become negligible. That's the term, okay, negligible. So that's why at the very infinities, we can throw all of that away. Just throw it away. So now I do take 3x to the 4. And now what I want to do here is I want to test for positive, let's do negatives first. For negative values, does that give you a negative or a positive number? Positive, right? So I say, okay, x equals -1, y equals a positive number. So here I say positive infinity. Okay? And then when I plug in like x equals a positive number, is y negative or positive? Positive, so I say positive infinity. And then in the end, this is my answer. Okay? All right, let's do that a little. Let's do the next one. Oh, no. Oh, I made a mistake. I just immediately assumed that's the first one. Is it the first one? No, it's this one. Okay? -2x to the 5th. I fell for my own trick there. Huh? Okay, in this case it's the same, but what if that was a positive 2x cubed, right? What if that was a positive 2x cubed? Then it would not have been the same. Okay, so the limit as x approaches -infinity of f of x, and the limit of f of x as x approaches positive infinity. So when I put a negative number in there, is y positive or negative? Positive. You see how I don't even care about the value? I just care about positive or negative. So this is positive infinity. And then if I put a negative number in there, a positive one, y is negative. Okay? Are we cool? 1 second. Okay. Now, here's something else that we have gone over. X-intercepts. We're going to keep talking about this. It's never enough. To find x-intercepts, set f of x equal to 0, solve for x. Okay. Finally, for the forever, now we're going to know. What are x-intercepts? X-intercepts are the zeros, or the roots, or the solutions. And those are where the graph does what? Yep, cross the x-axis. So here and here. Because how do you find x-intercepts? F of x equal to 0. You set f of x equal to 0. What's another word for f of x? Y. So those are all the points where the y value is what? 0. And when the y value is what is the graph doing? Crossing the x-axis. You see how it all fits together? It all fits together. Yeah. Okay. Okay. So now, zeros and turning points. Okay. So what are turning points? Turning points indicate where the graph will do what, do you think? Turn around. Turn around. Where the graph of a function changes from increasing to decreasing. So it's increasing and then it turns around. It's decreasing and then it turns around. So here, where is the graph turning around? In that little part right there. Okay, so there is a turning point right there. There is a turning point right there, and then there is a turning point right there. Yeah.
I can't tell, but is that middle one something that
It is, yes. I should have. Okay, so the reason why I didn't highlight it is because then it would have covered the turning point. But
that is one.
That is one, yes. Yes. Because over there, y is 0. Yeah, and this is what this lesson is about. Okay, now take a look. Okay. The degree of the polynomial tells us the highest number of times the graph is allowed to cross the x-axis. Okay? So, look at this polynomial in this box here. I have 3x to the 6, 10x to the 4, blah, blah, blah. The degree of this polynomial is what? 6. If the degree of the polynomial is 6, the maximum number of times it can cross the x-axis is 6. Okay? allowed to cross x-axis 6 times. Okay? No. It's allowed 6 times. Max. Of those 6 times, it can cross the x-axis 0 times, 2 times, 3 times, up to 6 times. Okay? Now, turning points. However many x-intercepts it's allowed to have that number minus 1 turning points. So, if the degree is 6, it has a maximum number of 6 x-intercepts and 5 turning points. Okay? It can use up all the 5 or it doesn't. It's like bathroom passes. You can go up to 3. You can use all 3 or you don't, but it doesn't roll over to the next function if you don't use it, right? That's what it is. Yep. Okay, so maximum turning points is 6 minus 1 equal to 5. Okay? So, the way we say it is not how many times it's allowed to cross the x-axis, maximum number of possible real zeros. Okay? So here we want to state the number of possible real zeros and turning points, and then we have to determine all of the zeros. Okay. Well, no, I'm not asking you for that. Okay. So, what are we doing here? Okay. So what is the degree here? 3. So if the degree is 3, therefore, 3 possible zeros and maximum 2 turning points. Now, let's find all of those zeros. So there could be at most 3 zeros. To find the zeros, I want to set f of x equal to 0. So that means the function has to be set equal to 0. I'm going to graph this, factor. Okay, so let's factor some more. This is going to be x plus 4, x plus 1. So x is 0, negative 4, and negative 1. So degree is 3. We got 3 zeros. It's possible, okay? All right, let's do another one. What's the degree? 4. So maximum zeros is 4. And turning points, how many? 3. Okay, now I want to factor this. So I've written quadratic form here. This is a quartic function, x to the power of 4. But we can still factor it like we factored this. Why were we able to factor it like this in the previous problem? It's because we had x to the power of 2, then x to the power of half of 2, 1, and then nothing, right? So here, when you have, look at what you have. You have x to the power of 4, then half of 4, then a constant. Okay? That's allowed. You did this in algebra 2, right? Yeah. So now, instead of x and x, we will have x squared and x squared.
Oh, like
yep.
U, right? If you said x squared equals u, right?
You can do that, but yeah.
Think about it like this.
Like a substitution. You can do it using substitution, yes. Okay, so minus 3 and minus 5. And now, These are all equal to 0. So x squared minus 3 is equal to 0. X squared minus 5 is equal to 0. X squared equals 3. X is plus or minus root 3. X squared equals 5. X is plus or minus root 5. Does that work? How many zeros did we get? Is that allowed? That's allowed. And whereas in the previous example, we got integer zeros, now we got 4 irrational zeros. And you know what? Irrational numbers are still numbers. Okay, let's do the next one. Look at the pattern. I have to the power of 4 to the power of 2. So basically, x to the 4 is the square of x squared. So it could be any pattern like that. It could be x cubed and x to the what? Square. 6. It could be x to the 5, x to the 10. And you can factor it the same way. So now, let's factor x squared minus 3 and x squared minus 1 is equal to 0. So x is plus or minus root 3 and x is plus or minus 1. So again, 4 zeros. Okay, and 3 turning points. I forgot to write that down for you because I got carried away with factoring. Yeah. Okay, multiplicity. Yep.
Are we gonna get any that have like more than 4?
You can't have more than the degree. It's not possible. It's mathematically impossible. Huh? You can't get more. If the degree is 4, it's mathematically impossible to get more than 4 zeros. You can get 3. Yeah. Eventually, yes. Okay. Let's talk about multiplicities. Okay. If a function has repeating zeros, all right, the multiplicity of a function is the number of times a 0 repeats. For example, take a look at this. F of x is equal to x squared plus 10x plus 25. That's a parabola, nice safe little function, okay? I factor this, and this one factors as x plus 5 squared. Okay? How many zeros is this allowed to have? 2. The 0 I get is x equals negative 5. That's only 1. How come? Because it repeats twice, right? If it's x plus 5 squared, now I don't want you to write it like this, but technically it's x plus 5 and x plus 5. It repeats, so it's x equals negative 5 twice. Okay? Decades ago, we used to call it a double root. Now we call it a repeating 0. Okay? But basically, because this repeats twice, I say it has a multiplicity of 2. And how do I know that? I know that from this step. I had x plus 5 squared. That tells me this shows up twice. So it's a multiplicity of 2. So those are my 2 zeros. It must be accounted for. Now, what does this mean if zeros are where the function crosses the x-axis? This one, if it's x plus 5 squared, 1, 2, 3, 4, 5. Here is negative 5. That's how it looks. So it crosses the x-axis 1 time. Okay? It could cross up to 2 times. That's what we said. Okay, so now, here is the thing. If a function has an x-intercept of even multiplicity, Like here we had a multiplicity of 2. That's an even number. Then the graph touches the x-axis at that 0 and then turns back around. You see that? This has a multiplicity of 2. So when x equals -5 was a 0, it came to that point and then it turned back around. Okay? If the function has an x-intercept of odd multiplicity, then the graph crosses the x-axis at that point of intercept. So if this was x plus 5 cubed instead of squared, this would have looked like this. At -5, right, the graph will come, not turn around like it did before, but cross. This is cool stuff. Okay. All right, let's move on here. Okay, here we're going to try to graph some of these functions without a calculator based on the leading term test, multiplicities, zeros, and all that good stuff. Okay, I'll get to you in a minute. Okay, first, now, so here's the thing. You need the function you have to use the function in both ways. This one has been factored for us. Okay? Sometimes you will get the function in standard form, then you have to factor it. So the thing is, for the leading term, you need the unfactored one, and then for everything else, you need the factored one. So you need both. But now, for the leading term, you know how we would take like, x cubed or, 3x to the 6? If it's factored like this, for the leading term, I take the leading term of each parenthesis. So I take the x, the 3x, and the x squared, right? So it's x, 3x, and x squared. All I need is the sign and the total exponents. So this is 3x to the what? 4. So now for end behavior, the limit of f of x as x approaches -infinity is what? Positive or negative? Positive. And the limit of f of x as x approaches positive infinity? Still positive. Let's look at the zeros and the multiplicities. Okay? From the first one, what's the 0? X equals 0. And then I have 3x plus 1 equal to 0. So x is -1/3. And then I have x minus 2 squared equal to 0. X equals 2. But what's up with that? Multiplicity of 2. So those are my zeros. Whoa, 3 zeros. Okay. Now I'm going to attempt to sketch a possible graph of this. Okay. I'll tell you where the difference is. There are some, we can do everything except the y value. The y value, like the location of the maxima and the minima. Okay. All right. So here's what we're going to do. We start with the end behavior. On the left-hand side, as x approaches -infinity, this graph is going up. So I put like a little guide arrow for me that it's going up that way. On the right-hand side, this graph is also going up, so I put a little up arrow there. Okay. My zeros are 0, -1/3. I'm going to zoom in here. Right there. And 2. Now, at 2, there is an even multiplicity, so it has to turn back around. So now, if my graph is going up on the left, then if I'm going from left to right, the graph is decreasing like this, right? It's going to decrease. When is the first time it's going to hit the x-axis? At negative 1/3. And when it hits negative 1/3, is it going to cross or turn around? It's going to cross, but then has to turn around to hit 0 again, right? So here, it's going to come down like this. Because it's a 0 there, and it's an odd multiplicity of 1, so it has to cross. Okay. I'll tell you. So now it turns around, and it has to touch this, it has to hit that 0. When it hits the 0, does it cross or turn around? Cross, because it's an odd multiplicity. And then at some point, it has to turn back around to hit the other 0, right? When it hits that other 0, does it stay or go back? I mean, does it cross or turn around? Turn around, and then it goes back up like it says with that arrow over there. Oh, that arrow over there.
I didn't know how far.
Okay, so the only thing that we can't know exactly is the location of the minimum and the maximum, and that you're allowed to guess. In calculus, you will know exactly where that happens. Okay? But for now, like, who would have thought you'd be able to do this, right? Like, before Precalc honors. I mean, like, look at this. This is impressive stuff. Okay, questions? Like, we know when the function is negative, right? Between negative 1/3 and 0. It's below the x-axis. It's positive everywhere else. I know where the function is increasing, decreasing, right? Okay? Okay. Okay, take a look at this one. Oh, my. This needs a y equals. Okay? Put a y equals quickly. Okay. All right. Leading term, what? What's the leading term here? Negative x to the 4th. So this one is not factored already, so I know like exactly what the leading term is. Okay, so the limit of f of x as x approaches negative infinity, and the limit of f of x as x approaches positive infinity. So look, this is an exponent which is even. So I know both ends will be facing in the same direction. If the coefficient is negative, then both will be going down. So I know that both will be going down to negative infinity here. I can either reason it out like this or plug in positive and negative values and reason it out from there. Okay. Now, I need the zeros of this. So let me set the function equal to 0. I'm going to factor out a negative x squared and get x squared minus 4x plus 4. This gives me negative x squared and then x minus 2 squared. So what are my zeros? 0, multiplicity of 2, and then 2, multiplicity of 2. Okay? Now, this function is going to negative infinity on both ends. Okay? The zeros are 0 and 2. So, from left to right, if it's starting from down here, it's going to increase and hit that 0, and then do what? Turn around. Turn around. Now, it has to turn back around to hit that other 0, right? And then do what? Turn around again.
So not like the maximum or the minimum, I guess, but like the minimum that you did.
They're all to
I made
minimum.
it low. Like you made it like I, for example, was like it doesn't matter how long you spend.
I'm not gonna require. You can't without calculus. You can't figure out where exactly it is. With calculus, you can figure out exactly where it is. Yes.
If there are two absolute maximums, like in this equation, would you say that they're relative maximums? Or would you say that they're absolute maximums?
In this, we say relative. It doesn't really matter. Yeah. Okay, find a polynomial function of degree n with only the following real zeros. More than one answer is possible. So, degree n is 4, okay? Which means it has to be, x to the power of 4. That's the leading term, right? And the zeros are 6 and negative 3. So now, here, when we had a 0 of 2, where did that come from? From a term, x minus that number, right? That's what gives us a 0. Okay? Ethan, did you have a question? Yeah. Uh-huh. No. Yeah. Coincidence. Okay. So here when I have a 0 of 6 and negative 3, my function, right? If you're going to write a function, you have to label it like a function. Okay, it has to be, the 0 of 6 has to come from a term that looks like x minus 6. Bear with me for a minute. Hang on. And then the negative 3 has to come from a term that looks like x minus 3 or x plus 3. Now I've fixed the zeros. Now I have to deal with the degree. I need this polynomial function to have a degree of 4. And right now, what's the degree so far? 2. So I have a couple of choices. One thing is this, right? That's one possibility. What's another possibility? Right, x minus 6, x plus 3 cubed, okay? Another possibility, no. So if you do this, now you also have a 0, right? X equals 0. And it says only the following real zeros. If you did x squared minus 6, right? That'll be x is plus or minus root 6, so that won't work either. Another possibility, if you want to like embellish and make it look pretty, you can put like a negative 2 out front. The constants don't matter. Okay? Minus. Right? The constants make no difference. All right? One of these, either one of these is the answer. So, whether you have to FOIL has to do with the instructions. If the instructions are just this is okay. If the instructions said in standard form, okay, then you multiply. Multiply, FOIL, distribute, whatever you, okay?